Oh yeah, you can put a halogen in the alpha position to a ketone. But why? Why do you care about that? Good question. Well, it turns out that alpha haloketones and alkyl halides in general, so like halogenated molecules in general, are versatile intermediates. So all that really means is that we can make a lot of molecules from halogenated molecules, whether that's by standard substitution chemistry or other chemistry that we're not necessarily going to touch on in organic chemistry too. Halogenated molecules are very useful. So anyway, we just learned about how we can, under acidic conditions, add a single halogen to the alpha position of a ketone. And essentially, if we then take that alpha haloketone and treat it with a strong nucleophile, such as sodium azide, again, how can we tell this is a strong nucleophile? Well, we have a charged N3 molecule. Azides are really useful for a variety of reasons. But that's going to do a standard SN2 reaction to replace that bromide with that N3. And really, many different types of nucleophiles, as long as they're strong nucleophiles, can just do a very straightforward SN2 reaction of that halogen. So that provides essentially any nucleophile we would want in that position, and in this case, it's N3. What else can we do? Well, we did substitution. What was the natural complement to substitution? It was elimination. How can we force an elimination here? Well, if we use a big bulky base, such as potassium terbutoxide, that will pull off the hydrogen in that beta position to the halogen. And after we treat it with that potassium terbutoxide, we will have an intermediate that looks like this. Why is that useful? Well, we could do addition chemistry to that if we wanted to. We can also do addition of different nucleophiles to this position here, the beta position, with respect to the carbonyl. So cuprates were an organometallic reagent that we learned about previously that specifically has reactivity where it'll add its group to that beta position, and this is a dimethyl cuprate. So if we added this dimethyl cuprate to this alpha beta unsaturated ketone, it would add the nucleophile to that position right there. And we would have the CH3 added there. I'm going to write plus/minus to indicate that technically that nucleophile added to the top and the bottom face. So it is in an enantiomeric mixture at that point. Really useful synthetic intermediates. Why do we talk about turning things into them? Well, halogenated molecules are not really readily available from the environment. So organic molecules, alcohols, ketones are often extracted from natural sources, and that makes them more available, but as kind of feedstock chemicals, but usually they don't have halogens on them naturally. So it requires an organic chemist to add the halogen to that molecule to kind of unlock the extra reactivity that a halogenated molecule can have. And in your course packet, the next thing says alpha halogenation of ketones and aldehydes provides functionalized alkyl halides that can participate in blank and blank reactions on the way to more complex molecules. All that was going to say substitution and elimination reactions on the way to more complex molecules. These methods allow us to add bullet point heteroatom nucleophiles to the alpha position and carbon nucleophiles to the beta position by way of these cuprates. That being said, we can also add carbon nucleophiles to that alpha position, and we can also add heteroatom nucleophiles to that beta position. It's just that that's not what I necessarily showed right here. We are going to learn more about making carbon-carbon bonds on the alpha carbon very soon.